These are the answers to homework 4F. Here are the definitions I would like you to know. And now to the questions. Number 1, complete the table for each of the following. So I've given you the reaction between nitrogen and oxygen forming nitrogen monoxide, and I've given you in the container initially 0.30 moles of nitrogen, 0.50 moles of oxygen, and no nitrogen monoxide. And you're to figure out what change is going to occur and then what the final moles will be. This is a limiting reactant problem, and in this case, the nitrogen moles will completely react away because they're reacting in a 1-to-1 ratio with oxygen. You're going to react away the exact same number of moles of oxygen, and because the ratio between the nitrogen and the nitrogen monoxide is a 1-to-2 mole ratio, you're going to form double the number of moles of nitrogen, so 0.60 moles of NO in this reaction. The key is the 0.3 to 0.3 to 0.6 mole ratio should exactly be the same as the 1-to-1 to 2 mole ratio in the balanced equation. The changing number of moles exactly equals the coefficients in the balanced equation. Subtracting or adding the columns now, you'll have no moles of nitrogen at the end of the reaction, you'll have 0.20 moles of oxygen, and you'll have 0.60 moles of nitrogen monoxide. In part B, the reactions between carbon monoxide and hydrogen to form methanol, and they've given you a container that's starting with 0.30 moles of carbon monoxide, 0.50 moles of hydrogen, and no methanol. In this case, if we imagine all the carbon monoxide reacts away, so it's going to be minus 0.30 moles, showing it all reacts. Because it's a 1-to-2 ratio, 0.30 moles of carbon monoxide would have to react with 0.60 moles of hydrogen. We don't have enough hydrogen to do that. 0.5 minus 0.6 would give you negative 0.1. That just means that all the carbon monoxide is not reacted away. All of the hydrogen must be reacted away. That's the limiting reactant. And because the hydrogen to the carbon monoxide is in a 2-to-1 ratio, the number of moles of carbon monoxide that will react has to be 0.25. The 0.5 to the 0.25 is the 2-to-1 ratio in the balanced equation. The methanol is in a 1-to-1 ratio with the carbon monoxide, so if you're going to react away 0.250 moles of carbon monoxide, you're going to form 0.25 moles of methanol. Adding up the columns, it's 0.05, one significant figure because the answer is 2 places past the decimal point. 0.05 moles of carbon monoxide when the reaction's over, no hydrogen, and you'll have 0.25 moles of methanol created. Question number 2. Hydrogen molecules and fluorine molecules are shown in the reaction container, and they react to form hydrogen fluoride molecules. Draw a picture of the chamber after the reaction has occurred. So the little red molecules are the hydrogens, the green ones are the fluorines, and for us to figure out what's going to be in the container after the reaction occurs, we have to write the balanced equation. So if hydrogen and fluorine are reacting with each other, the reaction will be H2 plus F2 yields, and the formula for hydrogen fluoride has to be HF because hydrogen makes positive 1 ions and fluoride makes negative 1 ions. To balance the equation, we're going to need a 2 in front of the HF, so this is our balanced equation. So we're going to try to predict what happens by doing the same thing we did in problem number 1. We're going to write initial moles, change in moles, and final moles, although this time we're going to apply to molecules. So initially we have 1, 2, 3, 4, 5 hydrogen molecules in the container, and 1, 2, 3 fluorine molecules in the container, no HF molecules. The limiting reactant in this case cannot be the hydrogen because I can't go minus 5 molecules of hydrogen and minus 5 molecules of fluorine. That would give me a negative 2. So the fluorine must be the limiting reactant. So the 3 molecules of fluorine will react in a 1-to-1 ratio with 3 molecules of hydrogen. And because the amount of HF is always doubled the amount of hydrogen or fluorine, you're going to form 6 molecules of HF. Add up the columns. Our final picture should have 2 molecules of hydrogen, no molecules of fluorine, and then 6 molecules of HF. And if you want to work this out a different way, if you think about the reaction, every time you have an H2 and an F2, they'll react to form a pair of HFs. So this H2 and F2 will combine together and change into a pair of HF molecules. These two will react together to form a pair of HF molecules. These two will react together to form a pair of HF molecules, and there's nothing else you can do. So this matches our results that we wrote down on the right side, remaining 2 molecules of hydrogen, and we've created 6 molecules of hydrogen fluoride. Question number 3. The reaction between iron 3 oxide and aluminum produces so much heat that it has been used for welding railroad rails in incendiary bombs and to ignite solid fuel rocket motors. If 15.0 grams of iron 3 oxide will be used in the thermite reaction, calculate A, the mass of aluminum that must react. So we need the balanced equation between iron 3 oxide and aluminum. So iron 3 oxide will react with the aluminum in an exchange reaction. The aluminum will replace the iron, and you'll get aluminum oxide plus iron. To balance the equation, we wind up needing a 2 in front of the aluminum and a 2 in front of the iron. To do the stoichiometric calculation, we're going to set up the problem by writing down what's given and what we're trying to figure out under the appropriate reactants and products. We're told 15.0 grams of iron 3 oxide, and we're asked to calculate how many grams of aluminum are formed. So these are the only 2 things we have to worry about in this problem, and what's important here are the coefficients in the balanced equation. This says 1 mole of iron 3 oxide has to react with 2 moles of aluminum. 1 mole of iron 3 oxide reacts with 2 moles of aluminum. That gives us an equality statement, chemically speaking. 1 mole of iron 3 oxide equals 2 moles of aluminum, and that's going to be the conversion factor between iron 3 oxide and aluminum. The problem gave us 15.0 grams of iron 3 oxide, so for us to use that mole to mole ratio, we have to always convert the given information into moles, and the way you convert grams into moles is by using the molar mass of the substance. Iron 3 oxide's molar mass is 159.70 grams per mole, so inverting it and then multiplying, we're going to wind up canceling out the grams, and now we'll have calculated how many moles of iron 3 oxide were placed into the reaction vessel. Now's the time where I can use the 1 to 2 mole ratio. The 1 mole of iron 3 oxide goes on the bottom, the 2 moles of aluminum goes on the top, and we have now calculated how many moles of aluminum you would need in order to react with the original 15 grams of iron 3 oxide. If they wanted moles of aluminum, the problem would be done, but if they want grams of aluminum, we have one more conversion we can do using aluminum's molar mass, and the molar mass of aluminum will be written such that the mole fraction goes on the bottom and the gram fraction goes on the top. Moles cancel out, and we will therefore predict that you would need 5.07 grams of aluminum in order to react with the 15 grams of iron 3 oxide. Part B says, what mass of aluminum oxide will be formed? So in this problem, we're going to solve for the grams of aluminum oxide. You can ignore this information here. So all that's going to be relevant is we're starting with 15 grams of iron 3 oxide. We're trying to find grams of aluminum oxide. The mole ratio that's going to be important in this calculation will be the mole ratio between the iron 3 oxide and the aluminum oxide, and it's a coefficient of 1 for the iron 3 oxide, and it's a coefficient of 1 for the aluminum oxide. So the equality statement we use in this calculation is 1 mole of iron 3 oxide equals 1 mole of aluminum oxide. So if I start with 15.0 grams of iron 3 oxide, I need to convert that into moles first. And now that I know the moles of the iron 3 oxide, it's a 1-to-1 ratio between the iron 3 oxide and the aluminum oxide. With the iron 3 oxide mole going on the bottom, the units will cancel out, and we've now calculated how many moles of aluminum oxide would have to be produced from the reaction of 15 grams of iron 3 oxide. If you want your answer in grams, you'll now use the molar mass of aluminum oxide, and if you arrange it with the moles on the bottom and the grams on the top, we'll calculate 9.58 grams of aluminum oxide will be produced. Now, instead of doing it, a calculation from iron 3 oxide to aluminum oxide, we could have started with our answer from part A, 5.07 grams of aluminum, and solve for Y grams of aluminum oxide, and we would use a 2-to-1 ratio, so either one of those calculations would have been acceptable. Part C, what's the mass of iron that would be formed? I'm going to once again start with the 15.0 grams of iron 3 oxide, but now my unknown is going to be for the iron. And the mole ratio here is 1 mole of iron 3 oxide will always produce 2 moles of iron, so the mole ratio step will give us the equality 1 mole of iron 3 oxide equals 2 moles of iron. So if we ignore the information for the aluminum and ignore the information for the aluminum oxide. The whole problem now in part C is only between these two outer substances in the balanced equation. Start with the 15.0 grams of iron 3 oxide, convert it into moles. Now use the mole ratio to get to whatever reactant or product you want, which is the iron. So I'll put 1 mole of iron 3 oxide on the bottom, 2 moles of iron on the top. Moles of iron 3 oxide cancel out. This will tell us how many moles of iron will have to be produced if you react away 15.0 grams of iron 3 oxide. To calculate grams of iron 3 oxide, just use its molar mass, and the final answer comes out at 10.5 grams of iron that would have been produced in this reaction. Problem number 4. Ammonia can be produced by the reaction of nitrogen gas with hydrogen gas. Calculate the mass of ammonia that would be produced when 750 grams of nitrogen gas reacts with 350 grams of hydrogen gas. So the equation here is going to be the reaction of nitrogen with hydrogen, and they're going to be forming ammonia, which is NH3. Hydrogen's diatomic, so it's H2, nitrogen's diatomic N2, and the product is NH3. To balance the equation, we need a 2 in front of the NH3 to balance the nitrogens, and then a 3 in front of the H2 to balance the hydrogens. In this problem, the given information is 750 grams of nitrogen and 350 grams of hydrogen, and that question is how much ammonia will be produced. This problem is different from the previous ones in that we're given the masses of 2 different reactants. That means we don't know which one will give us the right answer. We've got to get the answer from the limiting reactant. So this is a limiting reactant calculation. And when you do a limiting reactant calculation, you actually want to calculate how many moles of each of the reactants there are and set up an initial moles, a change moles, and a final moles table. So if we have 750 grams of nitrogen, we can use its molar mass, and the molar mass for diatomic nitrogen is 28.02 grams per mole. So therefore, we're actually starting with 26.77 moles of nitrogen in this container. The 350 grams of diatomic hydrogen can be converted into moles with its molar mass of 2.02 grams per mole. And so this container is being charged with 173.3 moles of hydrogen. So I'm going to erase my gram stuff at the top there, and I'm going to replace it with moles. And we're going to make an initial mole table with the change in moles and the final moles. So we have 26.77 moles of nitrogen and 173.3 moles of hydrogen. One of these is going to be the limiting reactant. You almost have to guess at first which one you think it's going to be. So let's just assume all of the nitrogen reacts away. So how much hydrogen will react with that? Well, it's a 1:3 ratio, so it's going to have to be 3 times this number. And the way you can officially calculate that is you take the 26.77 moles and multiply by the mole ratio between nitrogen and hydrogen, which is that 1:3 ratio. 1 mole of nitrogen, 3 moles of hydrogen, and that means that it would react with 80.31 moles of hydrogen, so that's the number that goes here. And because 173 minus 80 comes out to be a positive number, that means we've actually picked, luckily, the correct reactant to be the limiting reactant. So we're going to have 26.77 moles of nitrogen react with 80.31 moles of hydrogen, and now we have to predict how many moles of ammonia will be produced. It's actually a 1:2 ratio from the nitrogen. So if I just take my 26.77 and double it, that'll be the number of moles of ammonia that'll be produced. But if you want to do it officially, use the mole ratio between nitrogen and ammonia, which is 1 mole of nitrogen to 2 moles of ammonia. So that's essentially multiplying by 2. So we're going to produce 53.53 moles of ammonia. So in our change line under the ammonia, 53.53. The important concept, the ratios in the change line have to be 1:3 to 2, and 26 to 80 to 53 is 1:3 to 2. If we just subtract each of the columns or add them, whichever it is, we'll wind up having no moles of nitrogen left at the end of the reaction. We'll have 92.99 moles of hydrogen, and we'll have formed 53.53 moles of ammonia. And it's the moles of ammonia that's going to allow us to calculate the answer. We're just going to take the 53.53 moles of ammonia and use its molar mass to switch moles into grams. So a mole goes on the bottom, 17.04 grams on the top, and therefore we can predict you would create 912 grams of ammonia in this reaction. Question B, which one of the 2 reactants is the limiting reactant? It's the one that gets completely reacted away. That's the nitrogen. C, How many grams of the non-limiting reagent remain after the reaction is ended? Well, the nitrogen reacted all away, so the one that doesn't react away is the non-limiting reagent, and that's the hydrogen. So if you want to calculate how much hydrogen there is left over, our initial change in final table shows us that at the end of the reaction, we're still going to have 92.99 moles of hydrogen remaining. So if we take the 92.99 moles, use its molar mass to convert it from moles into grams, we can predict that you will have 188 grams of hydrogen left over in the container at the end of the reaction.